it should be working here. Okay, let's switch back to talking about our chapter 4. Okay, so chapter 4 we have a small review, so we will use this quite a lot. So we have this. Okay, so this is pretty hard. Okay, so we have this partial fraction expansion says that. So it's useful for doing. Okay, I guess it is not useful. Okay, so partial fraction expansion is useful for getting the inverse Fourier transform of a rational function. Okay, so rational function function of this form is a polynomial over another polynomial, and to do partial fraction expansion, what we do is first we factor the lower polynomial, so it's like x plus a, x plus b plus x plus c, so it has those roots minus a, minus b, minus c, etc. And this is then so you can always factor this just by because it's a polynomial, and then if all the roots are different and the degree of g is less than degree of I typo here. So degree of g is less than degree of h. Then so this should be degree of h. Excuse me. And the degree of g is degree of h. Then we can write we can have this partial fraction expansion. That is we can write f of x equal to this linear combination of partial fractions. So something over x plus a, something over x plus b, something over x plus c, etc. So each fraction for each root. Okay, and those ABCs they are not the polynomial of x anymore. They are just some constants, and those constants depend on the constants in the polynomial g and the polynomial h. And then you need to solve for ABC. Okay, and yeah, sorry, I have a bit of typo here. Okay, yeah, and so easiest way to do this is you multiply all these equations. So you multiply all these g of x over h of x equal to those partial fractions, and then you can solve for ABC. Okay, and then there is a special case. So we say that so when degree is g is less than degree h, it happens, and basically you can do nothing in terms of Fourier transform. And so let's assume this happens. And but when there are some roots not equal to each other, then we need to then we have those repeated roots. Then we need to do something extra. Okay, let's say we have a equal to b, and then we got x plus a squared here. Okay. And what we get is then we need to partial fraction expansion into term. Will expand into term like some a0 over x plus a squared. And then we need to have inverse Fourier transform of this thing. And we derive this inverse Fourier transform from this differential property this time. And we see that it's a bit like the exponential decay, but you have extra t here. So it is t to the minus at u of t. Okay, so that's a partial fraction expansion. And yeah, and then with this logic, we can get Fourier transform of almost any rational function. Okay, and yeah, so we have those examples, and then this will be useful later when we solve differential equation today. And now we go back to multiplication property we talk about. And so now you see this is a bit like what we have in the midterm. So you have two signals multiplying together, and in the time domain. Then in the frequency domain, you have this periodic convolution. Okay, and then we have seen this example. So this is kind of a carrier example. So we see that we have a quite arbitrary signal s of t, and you multiply with a carrier signal large as cosine omega t. And we see that in frequency domain, if your signal is a low frequency signal, then you multiply it with the carrier, then you get the carrier is a quite high frequency signal with omega 0 much bigger than omega 1. the resulting signal is this 2 copy of a high frequency signal. And yeah, so this way you can make your signal very high frequency. So you can pass on low pass filter, for example, pass on high pass filter, for example. And then you want to get it back, then you actually convolute with then you actually multiply with the same carrier signal once again. Then you see that you convolute this signal with this signal in a time domain. Then you get 1/2 the original signal in a low frequency one, and you have the 2 omega 0 and the minus 2 omega 0 signal, and those two you can be filtered out. Okay, and so that's kind of the idea of amplitude modulation. And so you have some mesh signal that's like low frequency. For example, it's a very simple low frequency signal, it's just some cosine signal here, and you multiply it with some carrier signal, it's high frequency, and the resulting is this amplitude modulated signal, because you can view the resulting signal as this carrier signal, but with the envelope that's your message signal. So message signal will determine the amplitude of your carrier signal. So the original signal, it kind of determines the shape here. Okay, although it's not totally the same because it goes to 0 and the amplitude never goes. This amplitude never goes to 0. Okay, and but anyway, so this is the idea of amplitude modulation, and we have seen some calculation in the midterm also. Although yeah, although we have done this with different ways of calculation as we shown. Okay. And then there's a question like think about yourself is transform from this x of t to y of t is this LTI system. Okay, and it's quite tricky. Okay, and that's the first example of multiplication rule, and let's see another example. And another example we don't see into detail, so we just kind of state here. Okay, so we have that x of t equal to sin t, okay, over pi square, pi t square. And then we want to find its Fourier transform. This is a more calculation result. Okay, and here we see that x of t is it's a really weird signal with 2 signs. But you see that it's in particular form, it can be written as the multiplication of 2 sinc signal. So it's a sin t over pi t times another sin t over 2 times pi t. Okay, and with extra pi. So you can view x of t as a multiplication of a 2 sinc signal. Then you know each of them will Fourier transform to a block signal in the frequency domain. And so the resulting big X of j omega, that's the Fourier transform of x of t, should be this periodic convolution of those two. Sorry, this should be it's not periodic convolution, it's just convolution. So it should be like this 1/2 pi convolution of those 2 block waves. Okay. And then you think about convolution of 2 block wave. Then maybe let's try to draw a bit of a picture here. So you will get like a block wave like this, and a block wave like different widths. Okay, so you have 2 block wave, and you want to see their convolution, and you see that their overlap will be. So when you have a partial overlap between them, then you get your convoluted result being this slope. And then you will have 4 overlap between them. Then you get this then you will get this constant region, and then you will get partial overlap between them. Then you will get this slope here. Okay, so you convolute this with this, then you will get this weird slope, plateau slope shape. Okay, so that's the multiplication formula. Any question? If not, then let's go to the. Okay, so we have some table about the property of Fourier transform, and you have seen that during mirror midterm, and yeah, those are nice properties. Okay, and some basic Fourier transform pair. And anyway, let's go to the next topic. So kind of the application of Fourier transform is solving differential equation. So system characterized by linear constant coefficient differential equation, we can use Fourier transform to solve them. Okay. So we want to use the differential property of Fourier transform to analyze those constant coefficient differential equation. And here is the formula or the equation of linear constant coefficient differential equation from previous chapter. So we have summation k ak dky dt k. So this linear combination of differentiations on y should equal to summation k bk dkx dtk, and equal to this linear combination of differentiations on x. Okay. And we try to solve this in chapter 3 by saying that you can just substitute x of t equal to e to a j omega t, and y of t equal to h of j omega e to a j omega t. And you can solve for h of j, big H of j omega. And here we do something similar and also get big H of j omega, but now with Fourier transform. So we say this thing equal to this thing, and assume the Fourier transform exists. We can Fourier transform both sides and use the differential property to get a nice expression of the Fourier transform here. Okay. So differential property says that when you get differentiation on time domain, you get HR j omega on the frequency domain. Okay. And so you differentiation k times, you just get j omega k times. Okay. And then you linear combination then, and then by the linearity of the Fourier transform is just a linear combination of those differentiations. So you just get summation k ak j omega to the k, and then the Fourier transform of your y of t. That's you just write as big Y of j omega. Okay. And similarly, the other side you get the summation k bk j omega to the k big S of j omega. But something interesting happen here is that you see this big Y and this big X has nothing to do with k. So the only part dependent on k is the summation k ak j omega to a k, and the summation k bk j omega to a k. And so you can take out this y and take out this x, and then you know big Y equal to big H times big X. So we just have big H equal to big Y divided by big X. So you move things around. This big Y divided by big X should be equal to this summation bk j omega to the k divided by summation ak j omega to the k. Okay. And and here is a bit of assumption take here. So we need to assume big H over j omega exists. So basically the system is stable. And we also assume we have the initial race condition. Remember that in chapter 2 we say solving differential equation we need then we need some auxiliary condition, and by picking initial race the system is causal in OTI. Okay. And so we are assuming the system is basically stable causal OTI, and that's with initial race condition. And anyway, we have this big H of j omega here, and by our Fourier transform, we have this big H of j omega. And then we look at how this depends on j omega. Is this linear combination of j omega to some power over a linear combination of j omega to some power. And so you see the upper part is a polynomial of j omega, and the lower part is a polynomial of j omega. So this whole thing is what we told ourselves today. It's a rational function of j omega. And so we can do partial fraction expansion on this thing. Okay. Usually. Okay. So if the system is nice, then you can do partial fraction expansion on this H of j omega. Okay. And let's see some example. Okay. And you do partial fraction expansion, then you can calculate US small h of t. Okay. And let's see some examples. So it's basically just the same thing with just numbers. So we have d squared y dt squared plus 4 dy dt plus 3y equal to dx dt plus 2x of t, and we try to solve this with the initial race condition. And bk J omega, now we just plug in the formula, so the summation bk J omega to the k, and bk are those things. And so b1 equal to 1, and you have J omega here, and b0 equal to 2 here, and over the summation ak J omega to the k, and so for the dy squared, d square y dt square, you get J omega square, and then with coefficient 1, and from the dy dt, you get 4 times J omega, and this 3 you got 3, so bk J omega, you just look at this equation, you can write it down. Okay, directly, and so far it's basically same as the chapter 3 thing you do. So you plug x and y with those things, with those two things into this equation, you will basically get the same result. But I guess here is a bit more direct. We have the explicit formula here. Okay, this is summation bk J omega to the k over summation ak J omega to the k. Okay. You look at this, and you put your ak and those ak bk J omega to the k into this equation, and then you get this bk J omega. And as we say, we want to do partial fraction expansion on this, and so you view J omega as your variable, basically variable x in our partial fraction expansion. Okay, let's try to, I think here. So this partial fraction expansion thing. So now we have this g of x over h of x with x equal to J omega. Okay, and so first we do factoring on the lowercase here. Okay, and we do factoring. We got so this example are set down nicely. So we got two roots here. So we have a root at -1 and a root at -3, and so you factor into this, and you get you factor into those two things, and you get then you do partial fraction expansion, so you get something over J omega plus 1, something over J omega plus 3, and then you just do brute force calculation here. You can get the coefficient here is 1/2, coefficient here is also 1/2, and then you can now do inverse Fourier transform from this thing. Inverse Fourier transform, you get inverse Fourier transform, then you get your h of t equal to this 1/2, and the inverse Fourier transform J omega plus 1 is e to the minus t u of t, and J omega plus 3 is e to the minus 3t u of t. Okay, and yeah, so that's a result here, and that's for example. Any question? Not? Okay. And then the second example is similar. Okay, so we have the same differential equation here, and we got same h of t, same big H, and then we got small h of t. Okay, and now we ask, so now we got this small h of t, and we ask if we input some x of t equal to e to the minus t u of t, then what's the output y of t? Okay, and then obviously there are multiple ways to do this. So first is you got this small h and small x, then you can just take those two signals and just calculate convolution. But now we are doing we are talking about a lot of Fourier transform, so we want to solve this with just Fourier transform and with no integration. And we can indeed do this by going back to the frequency domain. Okay, so we have h of t, and we have big H of J omega, and we know big Y of J omega is big H times big X. So first we have big X, but small x is a nice form we know. It also get this polynomial in J, rational function in J omega. Is 1 over J omega plus 1. Okay. And yeah, excuse me. And so x of t has this Fourier transform 1 over J omega plus 1. And so you multiply big H with big X, you see that it's still a rational function. So you get a rational function times a rational function and still get a rational function. So it's J omega plus 2 over j omega plus 1 squared times j omega plus 3. But now we see our repeated roots happening. Okay, so we have 2 j omega plus 1 root, and now this is an example of partial fraction expansion with repeated roots. So if you have second order term here, then you will, when you do partial fraction expansion, you will get 2 terms with this. So you will get this something over j omega plus 1 squared, and you also get a term that's something over j omega plus 1. Okay, and then you also have this partial fraction on j omega plus 3. Okay, so the repeated root, you have 2 fraction, and you can guess, hopefully you can guess correctly. So if you have higher order, then this is even more complicated. So you have like a third order root here, then you will have a first order term, second order term, and a third order term here. Okay, so more order over your root, then more terms you got in your partial fraction expansion. Anyway, so these are all the partial fraction. All the partial fractions related to this j omega plus 1 squared times j omega plus 3 is those 3 terms, and the coefficients we call them a11, a12, and a21. And here once again we skip the calculation here. You can multiply this out and say this thing equal to this thing equal to this thing, and solve for your a11, a12, and a21, and you will solve for these 3 constants. 1 over 4, 1 over 2, and minus 1 over 4. And then once again, you just apply inverse Fourier transform formula here. And this j omega plus 1 should give you e to the minus t u of t. And this j omega plus 3 is e to the minus 3t u of t. And then this j omega plus 1 squared is t e to the minus t u of t. Okay. And yeah, so that's how we get the output by going to time domain, by going to the frequency domain, do multiplication and the partial fraction expansion, and just inverse Fourier transform. Okay, and I guess this is basically the end of chapter 4. But we get some, so we will end early today, but there is something we'll talk about here. Okay, so this is not the end of a story of solving differential equation. So you see that we can get quite a systematic way to solve a linear constant coefficient differential equation here. But later, when we talk about Laplace transform, we'll do something very similar here. That's because, with Laplace transform, because basically we need, for all the things we do here, we need to assume we can do Fourier transform. And so I guess here I should write something more. So not only big X should exist, or big X, not only big H need to exist, so big X, big Y. So all those Fourier transforms need to exist for our for the thing we need to do here to make sense. Okay, and so for example, if our x of t is equal to say maybe our x of t, we can put a very base signal as input. Maybe we will want to put e to the t u of t. This is exponential ingrowing signal. But maybe just have another energy, and I want to see what happens if I have an exponential growing signal here. And then this signal is, this signal is not absolutely, this is not absolutely integrable, so it don't have a Fourier transform. And then this thing break down. Then you don't have this, because you don't have a big x of t that makes sense for this x of t. Then you cannot use this whole way, these ways to analyze your system input output. But you might think the signal, well, the system is still LTI if you have an initial race condition, and then you think what happens if I put this signal into this system, and what's the output? Okay, and so those are kind of question with unstable signal or I guess unstable signal is a weird term. Diverging signal or unstable system. We'll see how to deal with them with Laplace transform at chapter 9. Okay, so that's a bit of a cliffhanger that we'll deal with later in chapter 9. We'll see very similar calculation here, but with Laplace transform here on chapter 9. And but for now, we'll ask you some questions that shape out nicely, such that everything is stable, and we have all the Fourier transform, and you can solve some differential equation. You can solve some differential equation here. I guess in particular, so maybe if you set up your system, if your differential equation is not nice, then you can also get some unstable big H of j omega here. Say if one of your roots has instead of j omega plus 1 and j omega plus 3, maybe you have a j omega minus 1. And then we don't have a Fourier transform for j omega minus 1 because it give you we don't have the Fourier transform of 1 over j omega minus 1 yet, because if you put plus 1 here, then get E of t, U of t, and that's not a convergent Fourier transform. Okay. And those things will be dealt with later. Okay, and so I guess a very simple summary of this chapter. Then we talk about Fourier transform, and the most important two equations here are this Fourier transform equation and inverse Fourier transform equation. And let's read through them once again. X of t equal to 1 over 2 pi integration minus infinity to plus infinity big S over j omega e to j omega t d omega. And big S over j omega equal to integration minus infinity to plus infinity x over t e to the minus j omega t dt. And so this big S over j omega, we think about it as this x over t signal in the frequency domain. And it can be viewed as the amplitude of x over t e to a j omega t component. I guess times 2 pi from this expression here. Okay, and you can transform back and forth between x over t and big S over j omega if the signal is nice enough such that the transformation are convergent. And we also see that Fourier transform is very nice. It's very useful for analyzing LTI system because you see that this convolution formula, it will told you a very nice time domain and frequency domain relationship on your LTI system. It says that in a time domain, your output is the convolution between your input signal and this impulse response. And if you look at this equation in the frequency domain, you do Fourier transform on everything, then you see this you see this frequency domain output will equal to your system function big H, just multiplying with your frequency domain input. So in a frequency domain, output is just the system function of your system times the input. Okay, so this is quite cool. Okay, and so this is the end of chapter 4, and I think we are actually quite a bit ahead of schedule because this whole week is only for chapter 4. So I think we have leisure to stop early today, and we'll start on chapter 5 on Thursday. Okay, so if we don't have any question, then we'll stop now and see you on Thursday. Okay,